Okay, so in the previous class, we have gone through the fundamentals of design of water retaining structures. In that, we discuss the members subjected to combined bending and tension. Okay, so today we'll start with the another topic, that is design of circular tanks. Now, the circular tanks are used for water supply and sewage treatment plants. It is used for chemical processing, and it is also used for the large underground storage. Water supply and sewage treatment. Okay. It is used for chemical processing. Means, in uh, in chemical processing plants, and in for large and for large underground storage tank or storage or sump. Uh, the, sh- uh, the circular tanks are economical compared to other shapes because the perimeter of the circular tank is least compared to the other shapes. So these tanks are economical compared to other shapes. As its perimeter is the least compared to other shapes. For a given area. However, for the small tanks, the cost of the formwork for circular tank will be more, So for the small tanks, the circular tanks are not preferred, and the rectangular tanks are preferred. However, for small tanks, the cost of formwork for a circular tank is more, and hence rectangular tanks are preferred. Uh, Depending upon the type of the construction, the circular tanks uh, can be of two types, depending on type of construction adopted for circular tank. Uh, there are two types of tank. Uh, One is circular tank with flexible joints, between floor and walls. So in this type, the side wall is free to expand, is free to expand or contract as the joint between floor and wall is flexible. Means here, suppose we have a tank like this. Here, the sliding joint is provided. You remember uh, the joint. This type of joint is provided. Okay, so if you see the detail here, detail of this joint. This is this means this can slide. This can expand or contract. Okay. Here, this is the water level. Please turn off your mics. This is the water level. This is called freeboard. Himalaya, turn off your mic. This is uh, just wait for hold on. This it is hang. Now this is the water level. This is water level, and this is freeboard. And this is the diameter of the tank. and this is the depth of the water inside the tank. So this this is the type, one of the type in which the side walls, these are called side walls, and this is the floor. Okay, so the connection between the side wall and the floor is a flexible type. So such this is one of the type. Another type is in which this is rigid. Okay, so second type is circular tanks with rigid joint, with rigid joint between floor and walls. So in this type, the side wall is restrained to move by providing fixity or continuity with the base. So in this case, uh, this side wall, and the rafts are inbuilt. Okay, and the steel from the base or the floor goes into the side wall, and uh, proper anchorage is provided. So this proper anchorage is provided so that it behaves as a rigid joint. So this joint is a rigid joint. So with this, let us go through the theory of the first type of construction, that is circular tank with flexible joint between floor and side walls. So for this, let us consider this. So the pressure diagram due to this water inside the tank will be triangular in shape, just like the earth retaining structures, like retaining wall. The pressure diagram uh, is also triangular here. Here, this is H. So, in if you remember in the earth retaining structure, the pressure at the base of the triangle, the, the pressure at the base of the triangle is gamma. In case of the earth retaining structure, it is gamma S, means then unit weight of the soil. But here it is water, so gamma W times H. This is the pressure intensity at the base. This is pressure diagram. And if you see the deflected shape of this flexible type of tank, it will be uh, like this. This is the deflected shape, okay, and this is a pressure diagram. This is the water level, okay, and this is the freeboard. Okay, and here the sliding joint is provided, and the thickness of the wall is, let us say, T. Okay, because whatever the formulas we derive that will consider the wall thickness as T. And the this tank deflects from AB to AB dash. Okay, this is the deflected shape, and this is a figure of, or we can say, elevation of a circular tank with flexible joint. So because it is circular in shape, it will be subjected to hoop tension. So, and the intensity of the hoop tension will be maximum at the base. Okay, if you see it in the plan, this tank is actually circular. So in plan, this tank is circular. And because of the water inside, it will be subjected to hoop tension. This is the pressure diagram, and at each of these, the if you take a section here, if you take a section like section here, then this type of pressure distribution will be there. Means intensity will be zero at the top of the water level, and the intensity will be maximum at this level. So likewise, it will have pressure in all. So we can now, because of this internal pressure from the water inside, it will be subjected to hoop tension. The circular tank is subjected to hoop tension because of water pressure inside, because of water pressure. Okay. So and this hoop tension, this hoop tension is maximum at base. So at this location, the hoop tension will be maximum. Okay, here. At this location, uh, you have maximum hoop tension. Maximum hoop tension. Now, the maximum hoop tension at the base is given by this maximum hoop tension maximum hoop tension at bottom, maximum hoop hoop tension at bottom per unit height of wall per unit height of wall. It is given by gamma W times H, that is the pressure, multiplied by D by 2. So this is the maximum hoop tension at the bottom. So and this hoop tension is maximum at the base and its intensity decreases as we go up. So the hoop tension tension decreases as we move from it decreases from bottom to top. So as we move from bottom to top, the intensity of this pressure distribution decreases, and hence the hoop stress also decreases, and hence hoop steel required for resisting this hoop tension can also be reduced accordingly, and hence hoop steel um, may be reduced accordingly. Means you can reduce the steel uh, uh, as we move up, and the hoop steel can be and this hoop steel is provided horizontally. The hoop steel is the main steel provided horizontally in the form of the circular ring, in the form of circular the form of circular ring, okay, or in circular shape we can say. And the vertical steel and vertical steel provided is your distribution steel. Okay, and this the main steel or the hoop steel is provided on outer side, and the distribution steel or the vertical steel is provided uh, on inner side, provided on inner side to facilitate construction, to facilitate ease of construction. Okay, that means uh, the circular, this is the hoop steel, okay, and the vertical bars, they are the distribution steel. This is in plan. We are looking this in plan. Okay, and in elevation, this is the and in elevation, this will look like this. The outer one dot is the uh, hoop steel. So this is the hoop steel. This is also hoop steel, and this is hoop steel. Okay, and this hoop steel resists all the tension, means all the pressure from the water inside, that is resisted by the hoop steel. And this vertical steel is just minimum steel provided. This vertical is the minimum steel. It is called vertical steel, which is provided basis on the basis of minimum steel. Vertical steel, which is provided based on the minimum steel. So this is in plan, and this is the section. And this steel is given by the hoop steel is given by ASH. ASH means the area of the hoop steel is equal to uh, this tension, hoop tension, this hoop tension. Okay, this hoop tension. We call this as T. Okay, so this area of the hoop tension is nothing but T divided by sigma st. From the earlier example, earlier theory, we have seen that the member subjected to tension only, the area of the steel is given by tension divided by the permissible stress in steel, permissible tensile stress in steel. So this T is nothing but your gamma W times H times D by 2 whole divided by sigma st. So from this you can find the amount of the hoop steel. Okay, and where sigma st is the permissible tensile stress in steel. Okay, and you can also find the thickness of the walls, this wall thickness. Okay, this wall thickness, uh, using the same formula which we have used for the member subjected to tension only, the thickness of the concrete thickness of wall or side walls T is equal to uh, total tension divided by, if you remember that formula, it is T divided by 1000 sigma Ct into 1 minus m minus 1 sigma Ct by sigma St. Okay, so using this formula, you can uh, find the thickness. Okay, or you can find the thickness using the table which we have. Uh, uh, this is presented in tabular form. Okay, okay. This table is this is the table. You can use this table to find the thickness. This is the same expression to find the thickness. Okay, you can use depending upon the grade of the concrete and grade of the steel. You can use this formula to arrive at the thickness. Another way, is you can use some empirical equations that is given by T is equals to 30H plus 50. This will give you thickness in mm. You can also use this empirical formula. Okay, to find the initial thickness. Okay, and another this is actually we have derived. If you remember, this is derived from this gamma T divided by T tension divided by 1000 T plus m minus 1 times ASH. This should be less than or equal to sigma CT, and sigma CT is your permissible, that is permissible stress in concrete due to direct tension. Direct tension. So and here the value of T is this gamma W H times D by 2. Okay, whole divided by 1000 T plus m minus 1 into ASH, and this should be less than or equal to sigma CT. So from this expression you can find this you can find this T. Okay, this T you can transform. So if you transform this, the expression will be of this form. Or you can use this. So if you put the value of T here, it will be gamma W H D divided by 2 into 1000 into sigma CT, or you can write 2000 here, 2000 m minus 1 sigma CT divided by sigma ST. Okay, so using this also you can find the T required, or you can use this formula. Okay, so we stop here. In today's tutorial class, we will take an example of a circular tank with flexible joint. Any doubt in this? So we stop here.